Hi, it's Eric Archer from Texas Instruments, and today we have Jessica Kohout, a biology teacher, who's going to take us through the topic of population dynamics. But she has a really creepy way of doing it, and I'll let her tell you more about that. Jessica, tell us about the population dynamics and how you're going to teach population dynamics to kids today.
Sure. Yes, population dynamics is a really cool biology concept, and why not learn about population dynamics by talking about zombies? So we're going to get into that in a little bit. Like, how does that make sense? Well, our driving question today are what factors affect the size of a population in an ecosystem? So if we think about zombies and the zombie apocalypse, we talk about how many zombies can a population hold? And so it's one of those things that might be really kind of fun and interesting and connect. And then from there, maybe then students can apply it to situations in their own ecosystems in their neighborhoods. But zombies are fun. And so here we have an example of the zombie apocalypse lesson from Stand Behind Hollywood. And I have two graphs here. And Eric, what is the difference between these two graphs?
Well, let's see. So the top graph, the one that it says zombies per weeks, it looks like the data is just sort of going up. Like it looks like it just goes on forever. And then the graph below that, the data, it's zombies per time, whatever that unit of time is. And it looks like the data goes up, but then it starts to kind of flatten out a little bit. Is that the difference?
Yeah, essentially, we have here two examples of population growth. In the top one, we're looking at exponential growth, where a population is growing with unlimited resources. And so if zombies have unlimited resources, their populations will continue to increase. And then the second graph at the bottom, we have where zombies are, something about the population is causing the rate of increase to slow down. And we'll talk more about what's happening in each of these specific types of graphs. So first, let's talk about exponential growth, which is that first graph. And in this first graph, this is again in ideal conditions and unlimited resources. So if we're talking about zombies, what are the things that zombies need?
When you say resources, do you mean humans that they eat?
Yes, they need food. So food is a resource. And so if zombies populations are increasing, they're eating their food. They have unlimited resources and plenty of humans to munch on. And so in this case, we have a time range of about 10 weeks, and our zombie population is increasing. And right now it's, getting close to about 60,000 in 10 weeks. And so we're going to apply an equation of the change in the population over the change in time is going to equal the max per capita growth rate times the population size. So we're going to be playing with this equation a little bit later on. But I wanted to highlight this equation because that's going to help us understand how the population grows. And we're going to be applying it to zombies in this case. So the other type of growth is logistic growth. And so that's where we saw that initial increase and then that rate levels off. And so this is where our population reaches what is called a carrying capacity. And so carrying capacity is that limit in which the population reaches where it can't be successful past that number. It's that those birth rates start to decrease and the death rate starts to increase. And so you're running out of those resources. That's the cap of those resources. So what are the zombies running out of?
Well, I don't know if this is a good or bad thing, but they're running out of healthy people to eat.
Yeah, they're running out of that food resource. So you see that they're reaching that carrying capacity based off of the amount of food that's available. And that's represented as K. And so we take that, that max per capita growth rate and that population size, and we multiply it by this proportion of carrying capacity minus the population over carrying capacity. And so if we think about those values, if our population or N is very small and our carrying capacity is very high, then our rate is going to be closer to 1 and we're going to be increasing very quickly. But as that population number N gets higher and our carrying capacity or K gets closer, or that N gets closer to that K, it's going to be closer to 0. And and that's where you're going to be leveling out in this top bar here. And so we're going to play around with some of these graphs so that we can hopefully make sense of it. And so I pulled some of these graphs from the zombie apocalypse activity on STEM Behind Hollywood, and just for my personal use in terms of this video to show you some of those really cool graphs in terms of exponential and logistic growth. And so you can kind of see the stages of the zombie as it goes and becomes our full zombie population. And in this activity, zombies are formed by a virus that's transmitted through air droplets. So it's a little close to home right now. And so what we see in this graph is that same one from before. So over 10 weeks, we see this increase of our zombie population. And then in the next graph here, I'm going to show you it's just going to be a different scale. So it's still 10 weeks, but we're only looking at around 700 in terms of our population. So if we compare to our 60,000 zombies versus our less than 900 zombies, we see this big change in scale. And so here in this first few weeks, week 1 through 6, it doesn't seem like it's growing too much. But when you're really looking at it a little bit more closely, that rate is really increasing at it's the same rate as here, but it just appears visually to be faster. And so approaching the data at a different scale is really important for students to visualize how these values change. And so what I like to do also is to put this information in a spreadsheet so they can play with it. And so I put in a spreadsheet here where I'm going to be looking at our weeks. And that's going to populate because that was in the previous chart here. And then our first week, we had 3 zombies. So we look at that ordered pair. It's 1, 3. So at week 1, we have 3 zombies. So I'm just going to put that from that equation, R times N. And I'm going to get rid of this right now. And so that's our first 1 and 3. But I want to populate the rest of my chart by adding in an equation. And so using spreadsheets is this great computational tool that students should have experience with. And so I like to show students how to add equations to a spreadsheet in order to help them understand the data that they're collecting. And so what I'm doing here is I'm going to take that this value, so that first week, and then I'm going to multiply it. So this is our N for right now, and I'm going to multiply it by the rate. And so we can find the rate by looking at these values. So we have got 1, at week 1, we've got 3 zombies, and at week 2, we have 9 zombies. So what is our change in zombies?
6 zombies were added in 1 week.
Right. And so 6 zombies were added in 1 week. So we can take this and put it in a spreadsheet. So we have the weeks, we can then look at the rate. So if we're starting out with 3 zombies, we can then add in an equation. I feel it's really important to give students an opportunity to play with spreadsheets, manipulate spreadsheets, and understand what's going on by playing with some of these numbers and using equations to represent what's happening. And so if 3 is our first zombie, we're going to take that first zombie. So I'm going to click on B1 to represent our first week of zombies. We had 3. And then we're going to multiply that by the rate. So it's R times N. And so this is our N, so our R, let's start with 3, and that would give us 9. And so we can then drag this then down to see how that would affect how many zombies we would create in a given period of time. Or I should say zombie, I'll do N, we'll name it that. And so if I move down a little bit further, I'm going to drag this all the way down to, we have now 9, and I think it was 10. And then we can use this spreadsheet to make another graph. So I'm going to hit Control and Doc, where I was, and then I'm going to add a data and statistics page. And I'm going to graph our weeks versus our zombies N to see how our exponential growth works. I can also then go and change what happens here. So let's say our zombie are increasing at a much higher rate. So let's say at 5. And so we can take this and drag this down. Oops, too far. Get rid of that last one. And it increased significantly. And we can see that in our graph here as well. So actually, I need to zoom on our data. We're not even seeing all of it right now. So if I zoom in our data, our zombie numbers have increased quite a bit. So we went up to, I think our max was around 60,000, and now we're pushing up to 6 million. So by changing the rate and looking at what's happening here, we're seeing a much bigger number based on how the rate changes. And so by manipulating those values in those equations, you get to see a little bit more of what's going on. And so hopefully students can get a better computational understanding of what's happening within that data. With logistic growth, it gets a little bit more complicated because we're adding in that carrying capacity. And so when we are using our zombies, so let me play our zombies here. So we've got 2 visual representations. We've got a data table, I'm sorry, not a data table, a graph on the right that's showing how the zombies are increasing over time. But on the left, we're also getting data too. We're having these red squares up here. And what are those red squares representing, Eric?
Well, it looks like the red squares are people who have been infected and thereby turned into zombies.
Yeah, so that, it's not a traditional data table or graph, but it is providing information about what's happening. And so giving students access to different ways of representing information is also a very valuable tool. Seeing that those squares turn red, not all of them, there's still some humans left, but our population here.
Oh, so are those white squares that are left, those are the healthy humans, right?
Mm-hmm.
So
yep.
Those are the only resources that are left in that population.
Right, and there's not a lot left. So the zombies have kind of leveled off. They've reached that max and reached that carrying capacity because there aren't as many resources there for them. And so again, using a spreadsheet, I've got time. And so to put time in here, I've already pre-populated it to make it easier on myself. But I added the equation A1, which is time 0 plus 2. So I'm increasing that time increment by 2. And so I can then drag that down. So let's do to maybe about 20 time scale. So whether we're talking about weeks or seconds or months, we have to decide that. We have a rate of 1 right now, and then our N is going to be our C1, which is our initial population, times F1. And I'm going to change this over to the computer view on the teacher software, just because it gives a better idea of what's going on in the spreadsheet. And so you can see what's going on up here. So I've got time, which is T. We've got R, which is that R max rate. We've got N, which is our population number. Our K, which is our carrying capacity. This is that that proportion K minus N over K, and this is our population growth of dN over dt. And so for this one, for our N, we have to calculate it with our C1 plus F1. So we have to add in our population from F1 over here as it increases for each increment. Each time increment, we have to look at our population growth. And so we're going to add that in. And so we can start looking at if our rate is constant and our carrying capacity is at 10, this is what's going to be going on. And so we can see that our rate is increasing initially. So 2 is much higher than 0. And then what's going to be happening down here is that it's going to be leveling out. And so we can graph this again and see what's happening. So we can see this increase, and then where it's reached that carrying capacity, and then not being able to fluctuate much more. And so by playing around with either the rate or the carrying capacity, you can see fluctuations in the population. So let's make the carrying capacity now 20 and see what that does to our graph. And because we are now at a different graph, we're going to need to zoom in onto our data and see now that our population increases and then levels off. And we can change our rate to, let's say, maybe 3, and what happens. And so here, ooh, this looks messy. Let's see if it improves any here. All right, that looks very weird. But we can go back and change it back to, let's see what happens at 0.5. And then we get this kind of not a steep curve, it's a little smoother. And let me just make sure that all of our data is in there to make sure that we get a better representation of, and we are looking at very different curves based off of that rate and our carrying capacity. So by building a spreadsheet and getting kids to understand what those values represent in each of those categories, and then being able to manipulate those categories, they can see how that population fluctuates and what those, how carrying capacity is really important in a population, looking at what those resources are, whether they're available, and how the numbers of those organisms affect what's going on within that ecosystem. And so having that mathematical and computational thinking, relating it back to the data that they're given is really important. And from there, they can identify and make some connections with the organisms and how those reproductive strategies and organisms are needed, or what am I trying to say? That like how those changes in the populations are caused, whether they're density dependent or density independent. So whether they're K-selected species, where like humans, I would assume zombies as well, that where the birth rate decreases as the population reaches that carrying capacity because the death rate increases, and that's where the population is normally in, and that carrying capacity is fluctuating as around that carrying capacity, where the organisms tend to have fewer babies and take care of them longer. And those limiting factors are going to be dependent on the density of the population, such as food, water, shelter, and then predator-prey relationships are really important with that as well. And so with our zombies, they were dependent on their prey, which is healthy humans. And once those were gone, you know, that's where the population reached its carrying capacity. But then there's also density-independent factors and species where the birth rate and the death rate changes, but it doesn't affect the population density, or it doesn't change with the population density. And so with those types of organisms, like I think of weeds, where you have lots of offspring all at once, and then very few of them actually survive to adulthood. And so those limiting factors are density independent, which don't rely on population density, or things like climate change, natural disasters, which would then fluctuate the numbers based on external factors, not necessarily density. And so using zombies is a fun way to kind of relate to some of these concepts and give students an energetic way of learning about population dynamics.
Yeah, I've always heard that students, a lot of times after lunch, they kind of turn into zombies. I don't know. I don't know if that's true or not, but yeah, I've heard stories. Let's just put it that way. So
Yeah.
I love this lesson. I thought this was great. I like how you walked us through using, a fake organism, zombies, as a way to sort of, model a real life relationship. So an organism, a species can only increase its numbers so much. There's a limit to how much they can increase. And that's based on the carrying capacity of the environment, what it can, how much food is available for that particular species. In this case, it was zombies eating humans, which is super creepy. But the example still holds. It still makes sense. So great job. I love the lesson. And I've learned a lot about population dynamics and carrying capacity. Thank you, Jessica.
You're welcome. Thank you.